With each intriguing picture captured by the James Webb Space Telescope, it continues to gather insights from different corners of the universe, including planets within our own planetary system. A year earlier, we marveled at some of its most significant images, such as the Ken Cloud, the Stephan Quintet, and, strikingly, the charming Deep Field image. This expansive picture, in particular, portrays numerous galaxies resting within the vast scale of the universe, fulfilling questions that have been raised for ages. The James Webb Space Telescope has not stopped being a labyrinth of mystery. In fact, it has revealed objects that challenge deeply held cosmological theories. These astonishing discoveries are now being referred to as universe breakers by cosmologists, confounding established specialists with their ability to challenge existing theories. The reasons behind these discoveries remain shrouded in mystery, throwing our speculations and theories into confusion. So, what's the latest scoop from the James Webb Space Telescope? What amazing new revelation has it uncovered that was previously unknown to us? Join us as we dive into the discoveries of how the James Webb Space Telescope has introduced evidence suggesting the presence of another universe, testing the norm and understanding of the Big Bang. Our universe, as we've long known, rose from a hotter, denser state through a theory known as the Hot Big Bang. This idea, a significant scientific accomplishment over the last 100 years, gained overwhelming support during the 1960s with the definitive discovery of the cosmic microwave background (CMB), a remnant from the early hot and dense state. Over time, the Big Bang theory has remained the winning hypothesis explaining the origins of our universe. However, recent key insights have prompted cosmologists and astrophysicists to reconsider both the ongoing development of the universe and the Big Bang itself. Despite these challenges, alternative theories have failed to gain momentum, with the prevailing theory of the universe's beginning enduring. According to the dominant view, the universe began as a smaller, denser universe in the distant past. The presence of radiation such as photons indicates that the universe was hotter at its start and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels fluctuated, where a singularity could form and the laws of physics would break down around 10 to the power of minus 43 seconds. In such a short amount of time, tiny distances, brief timescales, and high energy levels challenge our understanding. Rewinding the clock to the speculative zero point, if the universe started as hot and dense, it would have expanded and cooled, producing large amounts of particles and antiparticles, with excess particles being annihilated by radiation. As temperatures decreased, the breakdown of the electroweak and Higgs forces led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions underwent development due to radiation pressure followed by gravitational collapse, resulting in the formation of large-scale structures. Around 380,000 years later, the discovery of the cosmic microwave background decades ago solidified the Big Bang theory as the most supported explanation for the universe's creation, describing the early universe as a hot, dense soup of subatomic particles gradually cooling over time. While most cosmologists and astrophysicists embraced the Big Bang theory, firm defenders of the steady-state theory, such as Fred Hoyle, continued to promote increasingly dubious ideas, only to face defeat despite overwhelming evidence. The proof presented was decisive. It wasn't darkening starlight or reflected heat from dust. The cosmic glow showed extraordinary consistency, resembling a perfect black body yet had no connection to known objects in the universe. Despite this, Hoyle and his partners continued to undermine scientific progress by supporting scientifically questionable ideas. Meanwhile, the fields of space science and cosmology underwent significant changes from the 1960s through the 2000s, with cosmology making especially important strides. We mapped the universe, described its large-scale structure, and studied the development, evolution, and dynamic interactions of galaxies and their cosmic populations. However, despite these advances, we encountered anomalies that challenged explanations within the framework of the Big Bang theory. Most notably, the absence of predicted relics such as magnetic monopoles or particles from grand unification led many to reconsider parts of the theory. The universe we observe today seems to require forces beyond our current understanding. Despite these difficulties, the expansionary model and its challenges persist. While existing theories fail to account for observed anomalies, two approaches have emerged: refine current theories or consider alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang model. Inflation proposes a brief period of rapid expansion that smoothed the universe, giving it uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and shifts, bolstering its validity. Nevertheless, despite alternative theories, inflation's scientific strength remains unrivaled. Roger Penrose's work, alongside his collaboration with Stephen Hawking, failed to match the development of inflation in explaining the earliest moments of the universe. Recently, efforts have been made to undermine the validity of inflation theory by supporting formal cyclic cosmology. However, this theory is inherently flawed from a scientific perspective, as the key difference lies in their predictions. Conformal cyclic cosmology suggests that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflationary theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang era. Cosmologists quickly took note of anomalies in the pictures sent by the James Webb Space Telescope beginning in 2022. These discoveries may require a reassessment of key aspects of the universe's origins and evolution. One significant discovery made by the Webb telescope was the presence of fully developed galaxies much earlier than anticipated by the standard cosmological model. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such revelations disrupt our understanding, much like encountering grandparents described as children in a story. Moreover, later evidence has revealed inconsistencies within major theories of the universe, such as the persistent error in determining the Hubble constant, which continues despite improvements in data accuracy and measurement methods. New data from the Webb telescope presents challenges to the current cosmological model. These issues highlight flaws within the model, raising questions among experts and physicists. While the model has undergone revisions recently to align with emerging data, some argue that these changes have been too accommodating. Thus, there is growing recognition that a shift in perspective may be necessary, possibly reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe during the 1920s. Subsequent revelations, such as the detection of cosmic microwave background radiation in 1964, confirmed the theory of the universe's origin as the most plausible explanation for the universe's beginnings, depicting the early universe as a hot, dense soup of subatomic particles steadily cooling over time. Achieving the current level of accuracy in cosmological understanding has required theoretical extrapolation beyond observational data. The possibility of infinite expansion, proposed in 1981, was suggested to resolve anomalies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid superexpansion shortly after the Big Bang. While specific issues are addressed by this theory, new challenges arise, especially given the prevailing belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Some recognizable anomalies, such as singularities within black holes, find support through indirect evidence. However, the stunning discoveries of the Webb telescope regarding the formation of galaxies and the ongoing issues with the Hubble constant raise concerns that we may be approaching a tipping point where a major revision of our current cosmological model becomes essential. This could necessitate a complete reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, deals with fundamental questions about the universe, its origins, and our place within it. The study of consciousness and quantum physics also explores similar topics, examining the intersection of theory and reality. It is important to reassess these foundational assumptions, given the impact of theoretical assumptions on data collection. History has shown that changes in scientific thought, such as the transition from geocentrism to heliocentrism or the discoveries of evolution and relativity, have led to profound changes in cultural perspectives. A similar shift in our understanding of the universe may be approaching, driven by an impending scientific revolution in cosmology. Scientist Robert Anton Wilson argues that theory becomes essential when further scientific inquiry fails to provide satisfactory answers to a question. Investigations into cosmology may ultimately lead to the breakdown of the current model, not due to observational errors, but because of its failure to embrace new principles that fully reflect the latest discoveries. The current narrative must therefore be reevaluated in light of new evidence as the James Webb Space Telescope continues to uncover discoveries that could forever change how we understand the universe. Neil deGrasse Tyson, a renowned astrophysicist and science communicator, made headlines with his comments on the James Webb Space Telescope, JWST, particularly regarding the discovery of evidence suggesting the possibility of another universe. The JWST, launched in December 2021, is a powerful space telescope designed to explore the universe in infrared frequencies, allowing scientists to peer deeper into the universe than ever before. Tyson's remarks stemmed from the remarkable discoveries the JWST is already making, especially in areas such as the formation of the earliest galaxies, stars, and exoplanets. While Tyson did not directly claim that the JWST has found evidence of a parallel universe, he referred to some of the puzzling and unexplained phenomena observed by the telescope, which could point to something beyond our current understanding. One such anomaly is the presence of strange, unexplained patterns in the distant universe, which might suggest that the laws of physics as we know them could be different in other parts of the universe or that the universe itself could be far more complex than we had previously imagined. This could imply the existence of multiple universes, as suggested by some theories in cosmology, such as the multiverse hypothesis. However, it is important to note that while these observations are intriguing, they do not yet provide concrete evidence of another universe. Instead, they open up possibilities for new theories and ideas that could redefine how we understand space, time, and reality itself. As the James Webb Space Telescope, JWST, continues to explore deeper into the cosmos, it challenges the limits of current scientific understanding and opens up new avenues for discovery. While we have long been constrained by our knowledge of space and its workings, the advanced capabilities of the JWST provide an unprecedented look at distant stars, galaxies, and phenomena that were previously out of reach. For example, its ability to observe in the infrared spectrum has allowed scientists to peer through cosmic dust clouds, revealing hidden details of star formation, galaxy evolution, and the behavior of black holes. This has brought to light previously unknown features and behaviors, adding layers of complexity to our understanding of the universe. A particularly intriguing aspect of the JWST's findings is its examination of galaxy formation. The discovery of fully formed galaxies far earlier in the universe's history than previously thought has left cosmologists questioning the standard models. The current paradigm, based on the Big Bang theory, suggests that galaxies took time to form as stars and black holes initially emerged. However, the evidence from JWST images appears to suggest that galaxies may have formed in a much shorter time frame, which could require a major rethinking of how galaxies come into existence. These anomalies are not just fascinating, they challenge core assumptions about the speed and mechanisms of cosmic evolution. Further complicating our current models are the strange patterns and fluctuations observed in the cosmic microwave background, CMB. The CMB, often seen as one of the cornerstones of Big Bang cosmology, may be showing signs of irregularities that were never expected by traditional models. For example, the uniformity of the CMB's temperature fluctuations has been called into question, with some observations hinting that it may not be as smooth as once thought. These discrepancies could be indicative of unknown processes or forces at play, potentially leading to a fundamental shift in how we view the early universe. In addition to the formation of galaxies, the JWST has also provided insight into the evolution of exoplanets. The detection of exoplanets is not new, but the depth of information now available has drastically increased. By examining the atmospheres of distant exoplanets, scientists can now assess their composition, temperature, and potential for habitability in much greater detail. This could eventually lead to the identification of planets with conditions conducive to life. The implications of such findings extend far beyond the search for extraterrestrial life. They raise questions about how life might arise in environments different from Earth and whether our current theories about the origin of life are too narrow. Another fascinating area of research that the JWST is helping to explore is the behavior of supermassive black holes. These cosmic giants have long intrigued scientists due to their immense gravitational pull and ability to distort the fabric of space and time. Observations from the JWST are allowing for more detailed studies of how black holes interact with their surrounding environments, including the galaxies they reside in. One of the most exciting possibilities is the role black holes may play in galaxy formation and evolution, as some evidence suggests that supermassive black holes are intricately linked to the growth of galaxies. Understanding this relationship could provide insights into the mechanics of the universe and help us better understand the forces that drive cosmic evolution. Despite the numerous breakthroughs provided by the JWST, the biggest mystery it presents may be its ability to challenge the very foundation of modern cosmology. As scientists continue to analyze its data, it becomes increasingly clear that there are gaps in our understanding of the universe that cannot be easily explained by existing models. This has led to the growing recognition that a new framework may be required to fully comprehend the vastness and complexity of the cosmos. Such a paradigm shift could have profound consequences for the way we perceive space, time, and the fundamental laws that govern the universe. The exploration of deep space via the JWST is not just about uncovering new knowledge about the cosmos. It is also an exploration of the very limits of human understanding. As we peer deeper into the universe's past, we are confronted with questions that challenge our most basic assumptions. With each discovery, we are pushed to reconsider not only how the universe works, but also how we, as human beings, fit into the grand scheme of existence. In this sense, the discoveries of the James Webb Space Telescope are not merely scientific breakthroughs, they are philosophical ones as well, urging us to rethink our place in the universe and the very nature of reality itself.